Okay, hello everyone. I'm Yusuke Matsushita from Kyoto University. And my collaborator is Hiromi Ishii from JIJ. Today, I'm thrilled to talk about our work, PLBorrow, where Linear Haskell meets Rust-style borrowing. Or maybe how Haskell can make better friends with Rust. To start with, I show you the big picture of this work. Software is the art of using computers to embody human ideals. This leads to two major programming paradigms. Imperative programming, geared towards computers, and functional programming, designed for human reasoning. Programming languages have evolved to unify these two paradigms, yes. A key language on the imperative side is Rust, which you have heard of a lot in this session. So roughly speaking, it comes from C and C++, and adding ownership types for high-level safety and robustness. And in a sense, this is moving towards functional programming, I would say. And another key language on the functional side is Haskell. Haskell is special in that it strictly guarantees purity. What's it? A program is pure if it gives the same result regardless of the timing of computation. So, it's like the computation going in the Platonic world of mathematics. Notably, purity is vital for predictable parallelism or concurrency, and also lazy evaluation. Recent exciting news is the birth of Linear Haskell, or Haskell extended with linear types, which is a kind of simple version of ownership type. This allows safe mutation inside pure computation and moving towards imperative programming, in a sense. So our work is going towards unifying the two paradigms, but can we go further? A key feature of Rust is borrows, or borrowing. It's a tricky feature to explain, but at a high level, it enables mutation without directly passing around ownership. So now we are ready to ask our core question. Can we safely and smoothly support Rust-style borrows in Linear Haskell, especially preserving purity? We answer this question affirmatively with our work, PLBorrow. At a high level, it enables purity, flexible mutation, and parallelism at the same time. Also, we have a case study of parallel quicksort to demonstrate. And it's implemented just as a set of APIs in Linear Haskell. It means that it readily works on the existing Haskell compiler GHC. And furthermore, we have a meta theory for PLBorrow focusing on the purity. To be frank, it's still kind of a work in progress, but it already has a crucial insight, I would say, which is a history-based model of borrowing that justifies purity. So here is a high-level comparison of PLBorrow with existing work. Compared with Haskell's core pure computation and SD monad, and Rust and basic Linear Haskell, our PLBorrow supports purity, mutation, and borrowing, parallelism, and leak freedom all at the same time. Okay, now we are ready to go into more technical details. First, I briefly reviewed Linear Haskell. In the original Haskell, data should be persistent for purity, and this can cause a lot of copying and mutation. For example, let's think of an operation that updates one element of the vector. This works like this. Unfortunately, we should also keep the original vector. So we end up copying the whole vector, which is bad for performance. Linear Haskell solves this by introducing linearity, which enables mutation in place. For example, the vector update operation can be typed like this in basic Linear Haskell. Here, the lollipop arrow is the linear arrow, which statically enforces the argument to be used exactly once. Thanks to this, we no longer need to keep the original vector, and we can safely use in-place mutation. Great. However, this basic style still requires you to directly pass around ownership. Can we do better? We can take an idea from Rust. Rust style borrowing. When there is a fully owned object, we can borrow it to create a mutable borrower, which temporarily gets ownership of the object, and a lender, or temporarily frozen owner. A key idea is to upfront decide on the lifetime or the deadline. During the lifetime, the mutable borrower can freely mutate the data. Remarkably, we can also split a borrower into smaller borrowers that borrow disjoint substructures, each of which can freely perform mutation. And finally, after the lifetime ends, the lender can safely reclaim the ownership of the object with a new updated value, which results from a series of mutations. Crucially, there is no direct communication from the borrowers to the lender for all this. This makes Rust style borrowing so special. Cool, so we want this in Linear Haskell, and can we really do that? We answer this question affirmatively by our work, PLDI'26. It introduces Rust style borrowing to Linear Haskell, remarkably just by adding a number of APIs to Linear Haskell. For borrowing, we have this simple function, borrow. This linearly turns an old object into a pair of a mutable borrower and a lender. Lin here is a witness that the computation is going in a linear context, but which we don't go into detail in this talk. During the lifetime, the borrower can freely mutate the data by various functions, including this modify that. Here we see the BO monad. This is a key mechanism we introduce, which I explain later. We can also split borrowers, for example, by this function, split at, which splits a vector borrower at an index. And crucially, you can drop or discard a mutable borrower at any time. Finally, after the lifetime ends, the lender can reclaim the ownership using this simple function, reclaim. The type class end alpha tells you that the lifetime alpha has ended. This might look simple, but actually quite magical, because we get the updated object without direct communication from borrowers to the lender. Our meta theory, which I explain later, justifies this. I briefly note here that our API design took a lot of inspiration from Rust-Belt's separation logic model for borrowing. But we also want to emphasize that we solved various unique problems for Haskell. Now, I explain the BO monad, a key new concept we introduce. BO alpha A means a computation of A that is allowed only during the lifetime alpha. This is used to enforce the timing constraint for borrowing, saying that each access by a borrower should precede the lender's ownership reclaim. Crucially, the BO monad can be run in a pure computation using this function, run BO. A key trick here is a rank 2 polymorphism to take a fresh lifetime alpha. This can actually be seen as a rich variant of the ST monad, an old, well-known technique to embed mutation into pure computation. And also remarkably, the BO monad supports parallelism with a simple function, per BO. It just takes 2 BO closures and executes them in parallel. Despite non-determinism by concurrency, per BO keeps the purity. This is because linearity guarantees the disjointness of mutations. As an advanced topic, I briefly explain sharing and reborrowing. We can temporarily share a borrowed object with this function, sharing. The type share stands for a shared borrow, which has only read access, but can be freely shared, just like in usual Haskell. And here, this is thanks to the non-linear arrow used here. A key technique used here is to take the lifetime intersection with a fresh lifetime beta to have a shorter lifetime. We can also reborrow a mutable borrower, which keeps a mutable borrower instead of a share borrower. Actually, sharing can be derived from a combination of reborrowing with the function share. Here, UR stands for unrestricted, which means non-linear, and thus shareable. So this way, PureBorrow supports quite a rich set of features for Rust borrowing, and further enables flexible combination of them thanks to Haskell's expressivity. Okay, now let's solve real problems. We conducted a case study of implementing parallel quicksort with our PureBorrow APIs. Here's a simplified code for our parallel quicksort function with a little idealized notation. By the pivot swap function at the 5th line, we can swap elements of the vector around the pivot value chosen for sorting in place. And this performs in-place mutation. This works in the BO monad, as you might notice. And by the split at function at the next line, we can divide a mutable borrow. And finally, we can recursively call qsort over each subvector and parallelize this with the parBO function. So this way, we enjoy performative parallel in-place mutation. As an advanced topic, to achieve better parallelization, we also implemented the work stealing scheduler, notably as a general purpose library extending PureBorrow. Please refer to the paper for details. In result, our parallel quicksort implementation successfully outperformed the naive sequential implementation. But our point is rather that PureBorrow is a useful abstraction for safe parallel mutation. As a scientific contribution, we built a meta-theory that works towards proving the purity of PureBorrow framework. The main challenge is how to justify the ownership reclaimed by the lender, which happens without direct communication from the borrower to the lender. Our solution is simple but new. The key idea is to build operational semantics on a history-based model. Because every mutation on borrowers is performed inside the BO monad, we can let the BO monad record the past mutation histories behind the scenes. And the BO monad can pass the whole history to the end lifetime token, which can be used by the lender to restore the updated value when it reclaims the ownership. Our main theorem says that our history-based operational semantics is strongly confluent, or satisfies the diamond property, over the choice of thread scheduling and evaluation order. One caveat is that we have not fully proved the purity, in a sense, in terms of referential transparency. This is because our semantics can generate fresh borrow IDs. Also, we should say that correspondence with this history-based operational semantics and standard memory-based operational semantics is quite a work in progress. Currently, we roughly sketched the proof strategy for progress by simulation by designing a dynamic relational linear type system, and completion of this proof is left for future work. I also want to briefly discuss a related work, OCaml, whose high-level motivation is similar to ours, but it's designed to require only lightweight annotational modes. This is great, but due to this, they only support core notional lifetimes, and they don't have purity. One interesting point is they distinguish linear and uniqueness. And we would like to say that our borrowing is actually a kind of non-aliasing in their sense. Please refer to the paper for details. Lastly, you can find our ViaBorrow bucket library on Hackage, and you can use it without any tweaks on GHC, so please give it a try. So this is a summary of this talk with a big laugh. Thank you.
All right, thanks, Yusuke, for the talk. Who wants to ask a question?
Hi, very nice talks. Thank you very much. So I've noticed that in a lot of functions here, like modify add and pivot, they all take immutable reference as an argument, but then return it. While yes. In Rust, you usually would not return it. You don't need to. You automatically get it back. So what is missing there?
Thanks for a great question. So it is possible to not to return the mutable reference. But if we do so, we would need to use a reborrowing function manually. Basically, we should do lifetime management quite manually in Haskell because we don't have borrow checker. So this is kind of like workaround to deal with the lack of automation in Haskell.
Maybe in the same vein, I noticed you have an explicit drop function for mutable references. So does Haskell not have affine types that you can drop automatically?
Yeah, exactly.
Do you think there's a chance they would add them to make this kind of stuff nicer?
That's actually a very good question, and I asked Linear Haskell people if they can add affine types, but it seems that it's kind of make type inference difficult because they support linearity or polymorphism or something. And if we add affineness, then the kind of algebra for linearity, affineness, non-linearity forms quite very, very tricky thing. So it seems that it's not easy to support for a while.
Okay, that brings us to the end of this very rusty session. Thank you all for coming, and let's thank Yusuke one more time.